The second test for positive series is comparison test. We have a theorem here say that if the series sigma an less or equal the series sigma bn, and if we suppose that this series of sigma bn converges or less than infinity, then the small series sigma an will converge also. It's logic, because if this term is less than infinity, so also this one is less than infinity. And always we suppose all of these tests for positive series. Okay, let's write a remark here. Now, if we suppose that this condition is correct, let's suppose that this condition here is or equal sigma bn, and let's suppose that sigma an equal infinity, or sigma an diverges. So because the small one is infinity, so this one also will be infinity because it's bigger or equal infinity. So sigma bn from 1 to infinity diverges. Let's take some exercises. Test the following series. So here we know that 2 power n plus 1 bigger than 2 power n. So 1 over 2 power n plus 1 less than 1 over 2 power n. So this series is less than sigma 1 over 2 power n from 0 to infinity. This is a geometric series with the base here is a half, the number a half between minus 1 and 1. Remember that the geometric series sigma a power n from 0 to infinity equal to 1 over 1 minus a f, the number a between minus 1 and 1. So this sigma equal 1 over 1 minus a half, so it's 2. So this sum is less than 2. So it exists, it's a real number. So my series here, sigma 1 over 2 power n plus 1 from 0 to infinity converges. So it's less than infinity using comparison test. Next exercise here, we can write 2n plus 5 over n power 3 plus 7. This is smaller than 2n plus 5 over n power 3. Then this could be written as 2n over n power 3, so 2 over n power 2 plus 5 over n power 3. So this series is less than series sigma 2 over n power 2 from 1 to infinity plus sigma 5 over n power 3 from 1 to infinity. And each one of these two series converges, so less than infinity plus infinity. So each one less than infinity. Why? Because remember the rule of the first test, integral test, and from the integral test, you know that sigma 1 over n power p from n from 1 to infinity, n from 1 to infinity, the answer will be less than infinity. It converges if the number p greater than 1. So here the number p is 2 or 3, both of them greater than 1. So both of them converges. So the addition converges. So now by uh, comparison test, using comparison test, my series here converges. The next exercise here, sigma 1 over ln n. So here, if we sketch the function ln n and the function ln x and the function y equal x. So from the sketching, we can remark that the function y equal x up and the function ln x down. So ln x is less than x for each x positive number. For example, what is ln1? What is ln1? 0, less than 1. What is ln2? It's less than 2. What is ln e? It's 1, less than e, nearly 2.7. So using this idea, and here, if n bigger than 2, okay, if n bigger than 2, so ln n less than n, and it's positive because n bigger than 2. If n bigger than 1, ln n will be positive because ln1 is 0. So from here, we can take the inverse. So 1 over ln n is greater than 1 over n. Now we can write this is bigger than sigma 1 over n from 2 to infinity. And we know that the answer here is infinity because sigma 1 over n power p from n equal 1 to infinity. The answer is infinity if p less or equal 1 using integral test. So now my sigma is bigger than infinity. So the final answer, sigma 1 over ln n from 2 to infinity diverges. Or we can write this is equal infinity.